Okay, so here in this video I've described the assignment which is in lab 2. So this is based on the data structures which we just covered in the lecture. So here you're going to implement the sparse matrix using a dictionary. So this assignment is actually probably not very well suited to be evaluated through HackerRank, but I have somehow managed it. So you might find that something is a little cumbersome, but the whole idea is that you will be able to get the essence of how the dictionary can be used. And I also want you to do coding in a particular manner which will help you modularize the code. So I'm sharing with you, this is the assignment, I'll come to it in a minute. I'm also sharing with you some skeleton code. So this I will upload it on Moodle. You can see the skeleton code which I have used here, and so you can see how what I've done is this code has got various functions, sm add, sm scale, sm trace, sm print. This is to print the sparse matrix, and this is your main program. Okay, so this code I've divided into multiple functions, and you have a main driver program which runs the code. So I want you to use this particular technique. This code skeleton has to be used while you submit your code on HackerRank. Now, for example, in HackerRank there is no main function because HackerRank itself has a built-in function which you have to edit, and the body of your program becomes part of the HackerRank function. So, in essence, that HackerRank function becomes your main function, and these other functions are supporting functions which your HackerRank function, or in other words your main function, will call. Okay, so the main program begins here. So you can there are some comments here which may or may not be relevant here because we are already getting the input in a particular manner. Anyway, so let's say once you are somehow you read the sparse matrix. Okay, somehow the matrix is specified and given to you, and then if you want to, let's say there are two matrices which you have added, SMA and SMB. Okay, you can do checks like make sure that the dimension is compatible for addition and all that. So but for this particular assignment you don't have to worry about it because the inputs I've given as HackerRank test cases are all compatible additions, so you don't have to worry. So now I'll tell you how the built-in these functions will be used. So there is this function which you have defined called sm add, which takes two sm objects. So sm object here is basically a dictionary. We have implemented the sparse matrix as a dictionary. So these two are dictionaries, and this function takes two dictionaries, and the underlying sparse matrices are added, and a new sparse matrix is created which is another dictionary, and that is returned to SMC. That is what it has to do. Okay, and if you want you can print the result. So this skeleton is not exactly how you do it. With respect to HackerRank, the printing may not be relevant. We will check the output in a different way. HackerRank will automatically check that for you. So suppose you want to write it as a standalone program, you can use these print functions too, so that you are clear that the matrix, whatever matrix operations you are doing, are correct. Here you can, there's another function called sm scale, which is scales the sparse matrix SMA by a constant k. And if you want to compute the trace of a sparse matrix, provided that it is a square matrix, then there is another function sm trace. So these functions which gives you back a int value. So right now for these examples and for this assignment, all the entries in the sparse matrix are integer values. So these functions sm add, sm scale, sm trace, you have to implement. Okay, sm trace, sm scale, sm add, all these are there in this function as a particular signature which you have to follow. It takes two sparse matrices and it returns a new sm as a dictionary. Fine, so you can go through the skeleton code. So use the skeleton code in your HackerRank program. Okay, because HackerRank actually checks only the output. It is, although I have told you here to use a sparse matrix as a dictionary, even if you use a list of lists, like how I showed you in the slide, and if the answer is correct, HackerRank will not be able to know that you have not done it the way I asked you to do, because it checks only the output, and if the output is correct, HackerRank will say your test case is passed. So to make sure that you don't do that, I will manually check each person's code. I will check to make sure that your sparse matrix is implemented as a dictionary. Okay, if you do not do that, I will not give you marks. The purpose of this assignment is to ensure that you understand how you can use the dictionary as a sparse matrix. See, there are some subtleties here which you have to take care. For example, if there is a sparse matrix of size 10 cross 10, out of which one entry is non-zero. Okay, it's a 10 cross 10 matrix. 100 elements are there, out of which only one element is non-zero. And suppose there is another 100 cross 100 matrix which also has one element as non-zero, and these elements are in two different locations of these two matrices. Maybe the first non-zero element in the non-zero element in the first matrix could be in location, let's say 1, 7, and the non-zero element in the second matrix could be in location 50, 2. Okay, now when you add these two matrices, the resultant sparse matrix will have two non-zero entries. So it will be a new dictionary which has two entries, two key value pairs. So that you must handle it in your code. Fine. Okay, so this is how this is specified in HackerRank, because I had to automate the process of code checking, of making sure that the output which you have created is correct. I had to do it in this particular way. So the input is given as three arrays. There is the first array SMA, the second array SMB, which are the two arrays which represents the sparse matrix. I'm using array here because HackerRank requires an array. HackerRank does not have a dictionary type built into it natively. Like the HackerRank submission system does not have a dictionary type. Okay, it supports Python, which supports dictionaries, but the inputs cannot be given as a dictionary. Inputs has to be given as arrays. So I have two arrays which represent the SMA and SMB, and one more array which gives you operations. Okay, this SMA has this particular format. SMA and SMB has the same format. So this array looks like this. The first two entries of the array tells you the number of rows and number of columns. The third element tells you the number of non-zero elements, and then followed by the non-zero elements themselves. So it will be of the form I comma j, which you also have to store the non-zero element and the location of the non-zero element. So I comma j a underscore 1, which is the first non-zero element, I comma j, which is the second the location of the second non-zero element, followed by the second non-zero element, and so on up to the n. There are nz non-zero entries. So ij comma a comma n a underscore nz is the ijth location of the nzth non-zero element. So this is the input array, and SMB is of the same type, and these are all integers. The array contents and the indices are all integers. The sparse matrix contains only integer values. Now that is SMA and SMB. Then there is also another array of strings which tells you what operations you must perform on the sparse matrix. So the array looks like the array of operations look like this. If there is an A in it, capital A, it means that you have to do this operation. SMA is equal to SMA plus SMB. You add these two sparse matrices and store the result into the same sparse matrix. Similarly, S means to subtract SMA minus SMB and store the result in SMA. R means reverse subtract. SMA is equal to SMB minus SMA. And CK is scaling. SMA is equal to SMA star K, where K is a scalar. So this is scaling of the sparse matrix, and you're storing it back into the same sparse matrix. And now finally, after these operations, so there are multiple operations in this last array. Once all those operations are done, then you have to return the sparse matrix in this particular format. The resulting sparse matrix, you have to return it in this particular format. Fine. So for example, I'll show you one test case. So this is how I've specified the test case in HackerRank. For example, this 15 here just means that the number of elements in that particular array. So this is the first array. Okay, it contains 3 is the first. There are 3 rows, 4 columns. There are 4 non-zero entries, and these are the 4 non-zero entries. 0, 2, non-zero entry is 6. 1, 1, it is 5. 1, 2, 4. 2, 2, 2. Fine. So this is the first sparse matrix. This is the second sparse matrix. 3 rows, 4 columns, because they have to be the same size. 3 non-zero entries. 0, 2, 2 is the non-zero entry. 1, 2, 2 is the non-zero entry. 2, 2, 5 is the third non-zero entry. This is the third array, which is the list of operations. The operations here are, there are 4 elements in this operation. C, 3, so that means you scale the SMA by 3. R means you do SMA is equal to SMB minus SMA. C6 here means you have to, whatever is the SMA which you have got, SMA is equal to SMA into 6, and A is add. Then you do SMA plus SMB is equal to SMA. So this is how I've specified the input. Okay, and the output which you generate is of the same format. The 15 here is not required. You will have to say the total number of rows, number of columns. That will still be 3, 4. This is just the sample output. There will be 4 non-zero entries. 0, 1. This is the first 0, 2. This is the location of the first non-zero entry, and the entry is minus 94. So these values I have got by actually performing this operation. Okay, I wrote the code which will do this. So this is what you have to do. I'm just showing you this so that you know how the output is specified and how you must provide the output. Try it on HackerRank. It is possible that I have made some mistake in some of the test cases, but hopefully if you find that as a mistake, please let me know. I have double checked it, but still it could be possible that there is still some bug. Okay. The second question is again similar to this, but here you are doing stack operations. This is a stack of strings. The explanation is given here. Here there is again a list of operations. P means push, O means pop, and M means multi-pop. That is, pop the top n elements of the stack. Fine. So you can read this. So this forms the assignment, and you can have a look at it, and you let me know if you have a question. We can discuss this more in the coming week.